Normally, I would cover disentanglement and information theory, but we spent quite a lot of time doing LLM lectures, so I had to make a decision and remove all the previous year's content that I think is out of date, and I wanted to spend more time covering up-to-date material. So yeah, I decided to cover reinforcement learning. Okay, so today we're gonna start discussing reinforcement learning and make extensions towards deep reinforcement learning. But before then, we need to underpin key concepts in RL. And last time we talked about diffusion models and its connections to NCSN and score-based models and connections to SDE and classifier-free guidance. It's basically giving contexts and latent diffusion to make it faster, as opposed to running diffusion steps in the image space. You want to run it in low-dimensional latent space. Okay, so I decided to break down the RL lectures into 3 different lectures. Today we're going to discuss the basic terminologies and Bellman equations and define what MDP is. And next lectures will cover model-free value learning, DQN, that stands for DQ learning. And then we're going to cover policy gradient and actor critic. So in today's lecture, we're going to make a key assumption that the model is given. Which is almost never the case in real life. It's completely unrealistic in real life, but still, regardless, we're going to assume it's given. And we're going to relax that assumption in the next lecture. What I mean by model is, in a current state, if I execute some action, I don't know how the world is going to turn out. It's stochastic, and yeah, it's hard to predict. And I don't even have the probability distribution on the next state. I can only sample once. And if I sample once, I can never go back, right? Okay, so today we're going to just cover basics. What Markov decision process is. So there's going to be a lot of definitions in the beginning. I'm going to define return, state value function, action value function, Bellman equations, dynamic programming, and optimality. Okay, so we have spent quite a lot of time discussing supervised learning. So we have some data and label. It comes from some data generating distribution, which we don't have the clear expression for, but we have access to the samples. And we want to formulate an optimization problem over the model parameter theta that minimizes the expected loss of our model with respect to some data, some label. So there's a fixed data set and immediate label for each data point, and how well or how poorly we perform on each data has no consequence. It does not affect any other data. So each data are independent. So if we screw up, I don't know, let's say I'm presented with a person image and I predict cat, it has no consequence on my ability to predict the next image. In contrast, in RL, I'm going to define what individual letters are in a second, but just giving you a high-level picture. The agent is in current state, ST. You commit on executing some action, AT. You're given immediate reward, and environment transitions you to next state, ST plus 1. And the objective, the optimization problem, is to optimize over space of all possible policies that maximizes the expected sum of rewards. So this is a discount factor. Let's just ignore this for now. So I want to define a policy or how I'm going to interact or navigate the world so that I can maximize the collection of the rewards from the current time step onwards towards infinity or some finite horizon depending on your environment. So whichever data you collect, what I mean by data here, this is data, this data, this data, this data, depends on your policy. So you influence which data you collect. Also, the difficulty is rewards may be delayed. So mathematically, we write it as RTST plus 1, but in real life, there are cases where this is 0 for all t. That is not the final step, and you have some reward only at the final step. So this is called the sparse reward versus dense reward. So this is another difficulty that makes RL very challenging. The reward is oftentimes sparse. So it's like saying you can imagine two childs growing up. Let's say they are initialized the same. Okay, so let's say we have a twin, and they are adapted to two sets of parents, and one kid gets constant feedback from the parents. If they do something good, they get rewarded. If they do something bad, they get penalty. And another path, they get no reward whatsoever. Then maybe you can assume, you can think about the outcome of two children in each path. So frequent rewards are good for learning, not just for agents, but for person as well. And actions, yeah, I already said this, affect the future states. Depending on which action you execute, your transition is affected. So think about an autonomous driving. You are turning a corner on a mountain path, and there's a cliff behind you. And if you go straight, you're going to fall off the cliff, and you're not going to be able to collect more data because you're dead. So which action you execute affects which data you collect. Okay. So it's really what happens if you execute this on game environment. It's really difficult to get a complete episode, meaning as you play the game with randomly initialized agents, you're never going to finish the game. You're going to die somewhere in the middle and not get to observe what happens after then. That happens especially early in the game. So RL, it's much more challenging than supervised learning. And I would say supervised learning is a solved problem now. You take, I don't know, 100 billion parameter model, you take a really large model, and you download, so here's the ingredient that people discovered. You take very large model, say transformers, download the whole internet, and train this giant model on lots of GPUs, and problem solved. Here, there are still algorithmic challenges because just because the problem is so hard, it's not like you can just download the internet and expect it's solved. Okay, so what's the setup? In this is still big picture. You have your agent that you want to optimize, and you want to train its policy. And you have a black box environment. So typically in RL, this is black box. If you input action to the environment, it's going to give you reward and your state, next state. So agent chooses actions. Environment returns reward and next state. So at each time step, this is policy. Policy is a conditional distribution on actions. Conditional on your current state, it's a distribution on your next actions. This may be deterministic or stochastic, but the basic setup is this is a probability distribution on actions. And the environment is a distribution on next states, condition on the current state, and the action. In real life, this is never available, but you can sample from this. You can sample, but you have no analytic form for this distribution. Also, reward is given from the environment. That's a setup, and you want to optimize this guy. Okay, so what are some examples? So let's say we have this cart pole. So here you have some metal rod and some ball attached to it. And your actions are you can push the cart to the left or right. And the state is cart position, velocity. So let's give it some names. This is x dot. X is position, x dot is velocity. And the angle is theta, and angular velocity is theta dot. And the reward is 1 while the pole remains balanced. So you want to balance the pole at the upright position where theta is 0. So how do you do it? By pushing the cart to the left and right at each time step. And the objective is, at a given state, choose the action to keep receiving the future rewards. So how are these given? In real life, nobody gives you this. You're supposed to design it, so you choose your own parameterizers of state, action, reward, and then so here's a discrepancy between real life and textbook examples. Textbook examples, state, action, reward is given, and you are learning the algorithm, RL algorithm, right? In real life, you do engineering to choose best representation for state and action and reward, and you just execute off-the-shelf RL algorithm like PPO and see how it works. So it's reverse. And what do people spend most time on is how we're going to define the state and reward. This is critical. In real life, this is never given. You're on your own to decide this. Has a tremendous effect on the agent's performance. Okay, so let's first define markup property. So a state ST has markup property if the future is independent of the past given the present. So the distribution, if the distribution of the next state given the current state is same as distribution of next state and current state and the past, then we say the state process has Markov property. So in order for the Markov property to hold, that means the state contains all the information needed to predict the future. In statistics, this is called sufficient statistic. Or in plain English, once the current state is known, the past history can be discarded. So in real life, as a RL practitioner, so in order for these RL algorithms to work, theoretically it relies on Markov property. So it really matters how you define your state. So depending on how you define the state, it may or may not be Markov. So in real life, you want to define the state so that it's very comprehensive. It's multidimensional, has all the necessary information, so that if you condition on your parameterization of the state, you'll be able to predict the future without conditioning on the past. So for example, if you're training an agent to play Atari games, then this would be a stack of image frame at time t, image frame at time -4, time -8, time -12, something like this. So you stack across the past temporal information to represent a state st. Okay, so what's MDP? So we're going to hear this word a lot. And MDP is basically a tuple of all these guys. S is a state space, A is action space, T is the transition function given by the environment, R is a immediate reward function, D0 is the initial state distribution. So depending on paper, you write it like this. Initial state comes from rho, where rho is the initial state distribution. Where distribution will be our initial state. So if you initialize the game, typically there's going to be a specific location where agent spawns or something like this. And gamma is a discount factor that discounts future rewards. So it's like having, I don't know, 1억 right now versus having 1억 10 years later. You discount 1억 10 years later, right? So this is discount factor that we introduce to sum all immediate reward plus next reward. As you keep adding the future rewards, you want to discount the future rewards and have basically the present value of all the returns. How do you compute the present value? Discount it by interest rate, right? Okay, so a policy is a distribution of actions given states. So given the current state st, the distribution on which action to take is defined as policy. And this is what we want to optimize for. So policy defines the behavior of the agent, and we're going to assume stationary policy, meaning we only look at what the state is, and we don't care whether it came from say st or st plus k. It's time independent. So it only depends on the current state, not the full history. And you may have a deterministic policy where you have a point mass distribution. So depending on your environment, this may be better than stochastic output. So what would be some environment that you can think of that stochastic policy is better than deterministic policy? Okay. How about when would be stochastic policy better than deterministic? Hmm. Can you come up with a concrete game that you play every day with your friends? Yes, exactly. So rock, scissors, paper, it's a game between the opponent and myself. And if I act deterministically, the agent, the opposite side, can figure out my policy and come up with better policy. But if I add randomness to it, then it's going to be very hard for the opponent to figure out my policy. And thus, there will be a Nash equilibrium that you can even prove the optimum policy is stochastic for rock, scissors, paper. So in that case, the environment is your opponent. Okay, so let's so another definition, trajectory. So for a finite horizon H, a trajectory is sequence of states and actions until the end. So you start from the initial state. S0 is a reserved letter. So initial state, action, environment transitions to next state, policy, samples, next action, and so on. And under a policy pi, the distribution on the trajectory, or the trajectory distribution, p pi of tau, is by probability chain rule. You can factorize it as following. First, state S0 is sampled from initial state distribution. Then, agent decides next action. Then, environment gives you the next state. And so on. It repeats endlessly. So the distribution on a specific sample trajectory can be factorized using the probability chain rule. So the interpretation is a trajectory is generated by alternating sampling according to the policy distribution and sampling according to the environment stochastics. Environment dynamics. Okay, another definition, return. So we already defined lowercase rt for immediate reward when we defined MDP. This is the lowercase r is the immediate reward. And uppercase r is reserved for return. So depending on which paper you're reading, some people write it GT, some people write it RT. So it's basically starting at time step t, sum of discounted rewards onwards. starting as t. What is your discounted sum of rewards onwards starting from time index t? So depending on your environment, you could have a clear time limit, i.e. finite horizon, or you might have an environment that has no horizon. So you could have infinite horizon discounted return. So you can probably see mathematically why discount was necessary. Without the discount, for infinite horizon case, this can sum to infinity. So we want to make sure we discount the future rewards so we don't get infinity here. Also, it makes sense in real life to discount the future reward. Because if I have 1억 right now, I could put it in the bank and get the interest. So 10 years later, it will have accrued that much interest. So the value of 1억 right now is much more than the value of 1억 10 years later. Right? So it's like 1 point interest rate, I don't know, let's give it 4%, 10 years times 1억. That's the future valuation of 1억 right now, right? So it's modeled through the discount rate. Okay, so what's the objective? So this is always a goal, right? We want to formulate some type of optimization problem at the end. What's our optimization objective? So in RL, there's a designated letter for the expected return of a policy. It's J, or depending on the paper, it's eta of pi. And it's nothing but the expected return, where the random variable is a trajectory, which is sampled from the trajectory distribution. So it's expected return, and we have defined the trajectory distribution here. You sample initial state from D0, action, sample next state, and onwards. Repeat. Okay, so expected return of a policy, that's what we want to optimize. So the central optimization problem in RL is search for this pi star, which maximizes the expected return of a policy. So the goal, once again, is to find the policy that maximizes the expected long-term reward. Okay, so we're not quite done with definitions. There are more to come. So first of all, state value function and action value function, or V pi of S, Q pi of SNA. So state value function, the definition is expected return conditioned on starting from state S. So conditioned on the fact that you start from this state here and act according to the policy, what is your expected return? That's the definition of state value function. Okay? You start from state S, that's given, that's conditioned, so it's not random anymore. That's fixed. You play your agent, interact with the environment, what is the expected return? That's definition of value function. Action value function, okay, it's set in stone. You start from star S, and it's also set in stone that you are going to commit to executing action A for this specific state. So you're in some state S, and you're going to execute action A, and then following the policy, what is the expected return? So you're conditioning on not only the state, but also a specific action for this state. So once you execute the state, you're going to follow the policy. This action here, this is only for the immediate state S. So you're in state S, you're going to commit to executing action A. and ignore the policy for now. And then environment is going to transition you to the next state, and then onwards you're going to follow the policy. What is the expected return if I do that? That's the action value function or Q function. Okay. So you're in some state S. You follow the policy to sample action A, and what is the expected future rewards? That's the definition of a state function, state value function. So in other words, V pi of S evaluates states, and Q function evaluates state and actions. So this specific combination. So what's the relationship between V and Q, or value function and action value function? So given a state, policy samples an action from this policy distribution. So by definition here, they're related. So V pi of S is actually expectation of the Q function where action, this guy here, is sampled from the policy. So if we sample action from this policy, Q, if we take expectation over A under the policy distribution, that's equal to the value function just by how we're constructing V and Q. They're related. And in case you have finite action space, we can explicitly write the expectation as sum of all actions weighted by the distribution pi. So the meaning is state value function V is policy weighted average of action values. Okay, so we defined V pi. So V pi Q pi follows the policy. Now we're going to define optimal value functions. So notice the notation difference. Here we have star. So optimal value function, it takes the V pi and maximizes over pi. So if we act optimally, then what is the expected value or expected return starting from state S? That's the definition of V star. Q star, if we act optimally, if we start at state S, execute action A, and then onwards act optimally, what is the expected return? That's the definition of Q star. So if we know Q star, the optimal deterministic policy is obtained by acting greedily according to the Q star. So if we have Q star, we immediately have pi star because at a given state, we can insert all actions and see which one has the highest Q value. So in other words, we have deterministic optimal policy where it's 1 if A is argmax of the Q star. So we insert all possible actions here, look up the Q values, whichever action has the highest Q value, that's the action we're going to take. Because by definition of optimal action value function, if we act optimally, we're expected to get that much return. Okay, so now Bellman equation. So remember, return is sum of discounted rewards. Let's just go back a little bit. So starting at time step t, following some policy, what is the discounted sum of rewards? That's definition return. So this return can be decomposed recursively. G of t, or return of t, is immediate reward RT plus discounted future return, one-step future return, just by definition. So similarly, the value functions satisfy the one-step self-consistency as well. So value is immediate reward plus discount times next value. Next value where state is defined sample from the environment. Right? So the value was expected future reward, but this can be decomposed recursively. So similarly, value can be written recursively. So for a fixed policy pi, V pi of S is expectation of action and next state of the reward plus discount times value of the next state. So values are related for a state S and its future state S prime, where future state is taken expectation under the environment dynamics, and action is a sample from, the expectation also takes, it also takes expectation under the policy distribution. So just stating the same thing. So B pi of S is by definition expectation of the return starting at state S, and this return is immediate reward plus discount times future return, one step future return, and plug that in here. So that's expectation of immediate reward plus discount future one step future return conditional on state S. So let's unpack this expectation a little bit. So this means we're starting at S, and we're going to take expectation under immediate action A. And then once we execute that action, environment dynamics is going to transition us to S prime. So this expectation here is also under next state. So this is action given S. This is expectation of the next state, S prime, plus the immediate reward plus discount times value of the next state. So this equation is called Bellman equation for the value function. You can derive the similar value function for action value function Q, all starting from our definition of return and relation of the value function with the return. Unpack it one time step, insert it, and you'll be able to come up with the Bellman equation. So value of the state S is expectation of the immediate action under policy distribution plus immediate reward plus discount times expectation under next state S prime and value of the next state S prime. Okay, same thing for the action value function. Condition on the fact that you start at state S, execute action A, what is the expected return? That's definition of Q pi. And unpacking it a little bit, you get starting at S, executing A, you get immediate reward RSA times discount expectation on their next state S prime, a value function of S prime. And we already talked about this. So value and action value is related. So value is starting as prime, following the policy pi. So if we take the expectation of the immediate next action of the action value function, that was the relation between V and Q. So insert this into equation above. We arrive at the Bellman equation for the action value function. So Bellman equation says action value starting in S, executing A, it's the immediate reward plus discount times expectation on their next state, expectation on their next action, Q value lookup of next state and next action. So we define the Bellman equation, and what about the Bellman optimality equation? So if we act optimally, and so the logic is pretty similar. So when we derive the Bellman equation, we started off inserting one-step decomposition of the return here, right? Here, we took expectation under the policy. But we said we're going to act optimally. So when we commit some action A, we get immediate reward plus discount, expectation on the next state, value function of the next state. But here, I'm going to replace it with one-step greedy action, where we take the action. So we insert all actions here, and take the action that has highest expected value. Same thing for the Q star. Let's compare this to Q pi. So here, we took expectation under pi, but here, by optimality, we're supposed to act optimally according to the Q. So here, the different part here is expectation under the policy has switched to argmax. So immediately you're set in stone that you have to execute this action, but onwards from then you have to act optimally. So state transition, you can do nothing about it. You have to take expectation, but next state onwards you're going to act optimally according to the Q. So the difference is Bellman expectation equation averages over the policy, but Bellman optimality equation maximizes over the actions. So also, if you look at the problem, there is a prediction and control. So prediction is given some policy. You want to estimate the value of all the states following the policy onwards. And control, you want to find the optimal policy pi star that maximizes the expected return. So what are some algorithms that solve this? So I said in the beginning, we're going to assume the model is known today. So there are two different methods. There's a policy evaluation method and policy iteration, value iteration. And if the model is not known, there are Monte Carlo-based method, TD learning, which we're going to cover in the next lecture, and SARSA and Q-learning. And deep learning version of this is called DQN. So how are we going to solve this? We're going to do dynamic programming. So we're going to assume the model is known. We have access to the distributions, environment distributions. which is in real life never the case. Okay, so what's policy evaluation? Given the policy pi, we can compute v pi by repeatedly applying this update. So value of a current state, any state, is expectation of action on the policy of immediate reward, discount times expected next state value. So this update does one step look ahead. So you want to look ahead into the future and compute some expectations and update your current V of S. So you randomly initialize your values in the beginning and repeatedly apply this update, and it's going to converge. Why does it converge? We're going to prove it towards the end of the lecture. It's going to converge to a unique optimal solution. All right, so suppose you have ran iterations on the values. So you can run this update for values or actions, and how do you choose the action? So once you have a converged set of QPy, so the algorithm is composed of two parts. One is policy evaluation, filling in the values of VPIs. This is to compute VPI. And phase two is policy improvement. So it's a two-step process. Given the policy, any policy, you fill in VPI using DP. Step two, you improve the policy. How do you improve the policy? Given the filled-in TP table for the Q state action values, for each state, take the action that maximizes the Q pi of S. Okay, you insert all the actions here. Your policy is now a deterministic policy where you act greedily according to your currently converged Q pi. Or equivalently, if you do value iteration, policy evaluation on VPIs, you can do Argmax of A, immediate reward plus discount expectation on the next state of VPI of next state. Or you can do policy evaluation on the Q directly and use this equation instead. But if you do VPI, you can still incorporate the optimal policy this way. Okay, so why does it work? So the intuition is if you know how good each action is on their pi, then choosing the best one should not make the policy worse. So we need some form of guarantee that this policy is better than what we started off with, right? So we started off with some random policy and filled in all the values for this table for all the states. And if we act optimally, we now need to check whether this policy is better than the policy that we evaluated the VPI on. So if we do one step greedy, is it better? The answer is yes. So here's the theorem. So this is policy improvement theorem. Let pi prime be greedy with respect to Q pi. So if we act greedily according to the learned value function, then we can prove that for all states, value for this one-step greedy solution is better than what we started off with, where it's going to be greater than or equal to. So we don't actually make it worse. If this is true, then what's the consequence? Okay. Can we come up with an algorithm? So let's say only thing that's given to us is these two guys, and we want to come up with, say, optimal policy. How do we do it? What's the algorithm?
For every action that we evaluate the Q pi of Q S comma A based on those key and R, then we can just choose A that maximizes the Q pi of S comma A.
So the algorithm is following. So that's correct. So here's the algorithm. You randomly initialize the policy. That's step 0. For that random policy, you run this iteration to fill in the values for all the states. Given your values that's filled in, you come up with one-step improved policy that acts according to the values. This is going to be better than the previous policy. So you have an improvement one step. Given improved policy, you recompute the values for all states. Given the recomputed values, you change your policy by acting greedily according to the currently updated values. Given the policy, you reevaluate the values and repeat. So you repeat between policy evaluation and policy improvement until the policy doesn't change. That's the algorithm to retrieve the optimal policy, assuming you have access to the transition dynamics and reward function. So you alternate between policy evaluation, policy improvement, until policy doesn't change. That's the algorithm. So in order for that to work, you need to prove you don't make it worse if you act according to the values. What else do you need to theoretically argue? Okay, any math majors here? Okay, so here's my claim. My claim is if I repeat this cycle many times until policy doesn't change, my claim is the end result is pi star, optimal policy. If I want to claim that in addition to this theorem, what else do I need? Upper bound for upper bound for Q pi, V pi. Is there a more direct answer? Right. So if I repeat this cycle 1 and 2 many times until policy doesn't change, you need to prove that this converges to a unique optimum point. Because it may be the case, it's often the case if you come up with this kind of algorithm, it gets stuck at a local optimum. So in addition to this, you need to prove state and prove if you repeat this, you're going to converge to a unique optimal solution. That's going to come later, but let's just try to prove this right now. So pi prime is the greedy policy that acts greedily according to the currently given Q pi. Then value of V pi for all states is greater than or equal to value of pi. That's the policy improvement theorem. So Q pi acts greedily according to pi prime acts greedily according to Q pi. So let's insert pi prime here in the action slot. So that's going to be, since this is greedy, here you insert all the actions, take the one that's argmax. So that's going to be greater than or equal to expectation of the Q over actions. Simply because we're going to insert everything and pick the one that's highest. And the right-hand side is equal to V pi. So Q pi of S and pi prime is greater than or equal to V pi of S. And let's invoke the Bellman equation for Q pi. So Q pi of S and this specific action, pi prime, is immediate reward plus discount times expectation under next state, value of next state. So from the equation above, V pi of S is upper bounded by immediate reward, discount times, I'm going to rewrite the expression here as following. I'm going to unpack here one step. So it's expectation of V pi of S1 given you start from state S, execute pi prime for this specific state. Right? We're committed that we're currently in state S, and we're going to execute pi prime of S. What is the expected return? That's the expression here. So you can probably see what's happening. For any state S, V pi of S is upper bounded by immediate reward plus discount times expected future value under policy pi, conditioned on the fact that you start at S and execute pi prime. So if we apply the same inequality recursively to all the future states while following pi prime, then we can conclude that value of V pi of S, or value following this policy, is less than or it's less than or equal to expectation under this new policy pi prime of all the future rewards that we follow from pi prime. And this right hand side is equal to value of following this new policy pi prime. So for any states, if we define this pi prime as optimal policy, one step greedy policy that acts according to argmax of Q pi, then we can say the value of the changed policy pi prime is greater than or equal to value of the current policy pi. So it doesn't make it worse. So this policy iteration algorithm is you randomly initialize the policy, evaluate by solving DP for all states, and then you do the greedy improvement, which acts greedily according to the learned or DP computed V table, and repeat. And you stop when the policy no longer changes. So it has two phases. Evaluation phase, where you fill in the values for all states, and improvement phase, where you adjust the policy to act according to the currently duly computed value tables. There's more direct approach where you do everything one shot, and that's value iteration algorithm. Unfortunately, it looks like we're out of time.